Well, hi everyone. In this video, I would like to spend some time giving you a basic introduction to the theory of planar graphs. These are very important. I mentioned in the past the fact that the applications are quite real world oriented here, from everything from computer networks to highway systems to electrical and plumbing systems of homes in a neighborhood. There's lots of applications of planar graphs. These are basically graphs where the edges don't cross each other, or at least they're graphs such that it's possible to draw the edges without them crossing each other. So let's actually start by writing that down again as the definition. So let's recall that a planar graph, a graph G, is planar, right? If it can be drawn so that no edges cross. Now, it doesn't mean that it's drawn that way to begin with, right? It may be necessary for you to redraw it. So, for example, I think I've shown this example in the past. It's a common one to work with, which is the graph of the complete graph K4. And the way I've drawn it now on the board, you see that there are crossing edges. Well, so it is possible to redraw that graph without that crossing edge, because I can take one of the edges that was in the center of this square and kind of just hook it around the outside so that it doesn't have to cross any other edges. And in that way of doing it, we now have what's called a planar representation of this graph. So good to keep that in mind. The graph may not always be drawn without crossing edges. The point is it can be drawn without crossing edges. Here's another example that might be interesting to you. If we look at the complete bipartite graph, so let's look at K of 3, 2. So remember how that works, that you have all of the edges going from the one camp on the left to the other camp on the right, but you don't have any edges within the two camps. Okay, so these are, this is a graph with quite a few edges as well, and you can see that the graph has lots of crossings in it the way I've drawn it now. However, we can redraw this one also with a planar representation. What I can do, guys, is just take one of the vertices from the camp of 2 and put it over on the other side of the 3. So here's the 3 vertices from the left camp. I'm going to leave one of the 2 vertices from the right camp over on the right side, but I'm going to move the other one over to the left side. So this is still the same graph. I've just simply, flipped half of the graph over to the left side of that sort of central axis so that there's no crossing edges in this graph now. Okay, so that's another example, and that's a planar representation. So, what you might be curious about, or a goal that we might have, would be to come up with some theorems about what kinds of graphs could have planar representations. It may not always be obvious, right? So do we have any theorems that say, G is planar if and only if, and, what could we put over here? It turns out that there is a really good theorem that we can put into this type, and that I'm going to share with you shortly. But it's a fairly deep theorem. It's a fairly involved theorem, so it takes a little bit of getting used to. So in the meantime, I want to start with some slightly easier results. So I'm going to start by focusing on sort of what would having a planar graph imply, right? So I don't have a theorem on the board yet. I'm just going to think out loud. If I assume that I have a planar graph, so that's a graph that has a planar representation, like what would I be able to do with that? Well, one thing to sort of note right off the bat, and we can see it in the examples of the planar representations here, is that planar representations sort of split up the XY plane, the two-dimensional space that the graph is drawn in, into regions, right? We have regions, like here you have region 1, region 2, region 3, and you could even call the outside of the whole picture region 4, right? Similarly down here, you have region 1, and then region 2, and then on the outside, region 3. So a planar representation will kind of create these regions that the whole XY plane is divided into. So let's just start with that as a note. A planar representation. A planar representation of G splits the plane into, I'm going to use the letter R, regions. It splits it into R regions for some value of R. I don't really know what that is yet, but that's the idea. There is a connection between the number of regions that you have and the number of edges in the graph. So if we go back to these examples again, you'll notice that each edge is sort of forming a boundary, is at least one of the boundary edges of two different regions, right? Whichever side it is on. So that's certainly true. So this edge is a boundary between regions 2 and 3. This edge is a boundary between regions 1 and 4, and so on. Actually, it is possible. It is possible. Let me draw one more example here so we can kind of look at it. It's possible that when you look at your planar representation, you can have an edge that's just kind of sticking into the middle like this. So here I only have two regions, but there is an edge right here that is kind of contributing twice, right, to the bound. It's considered to be contributing twice to the boundary of region 1 only. So it's not really a boundary of two different regions. It's a boundary within one single region, but it's sort of, you can think of it as being counted twice because sort of both sides of the edge are inside of that region, okay? So that's kind of just a little remark. Each edge contributes to the boundary. Each edge contributes to the boundary of two regions, or if it is an interior edge, which is kind of what I was just talking about. If it is an interior edge, it contributes, let's say, sort of double. So I'll say twice. It contributes twice to the boundary of one region. Right. Okay, so hopefully that makes sense. Now, guys, just before we get too far into this, I just want to be really clear that we only talk about these regions and boundaries of these regions for a planar representation. If I come back over here to one of these graphs, right, I don't want people to be thinking of these little crossing places as being boundaries of regions. Like this thing here doesn't really have well-defined regions. The regions are determined really by the vertices of the graph. There is no vertex here in the center of this square, so there's no regions here. So if you really want to analyze the graph in terms of how many regions it has, right, you need to do it in the context of a planar representation, not just any old representation of the graph where you could have unintentional crossings to begin with, right? So there's a big difference between working with this graph versus working with this graph, right? So we really want to make sure that it is a planar representation. Okay, well, with that as a basic background, I'm ready to give the definition now of the degree of a region. So let me see if I can do that. I might even steal a little space up here so that I don't have to erase all of these pictures yet, because they're pretty nice pictures to analyze. But let's put a definition up here that we can hopefully take advantage of. The number of edges forming the boundary of a region. Let me call the region capital R. The number of edges that are forming the boundary of any region is the degree of that region R, and we'll denote this as you might expect. We're going to denote this degree of R, DEG of R. So the degree of a region, right? So that hopefully kind of makes sense. So we could go through, you know, maybe I will just draw a new graph here. But actually, I'm going to, for my example, I'm just going to redraw that same K4. We'll just draw K4 again, but now I'm going to, instead of numbering the regions on the inside, I just want to get the degrees of the regions figured out. So you can see that, you know, on the inside of the square, we have, you know, a triangle. A triangle is basically a degree 3 region, right? You have 3 edges that forms the boundary of a triangle. So here's another degree 3 region. And even this one, you have the one curved edge and then the 2 sides of the square up here. That's 3 edges total. So the degree of that region is also 3. If I go to the outside exterior region, well, that one, 1, 2, 3, that also has degree 3. So in this picture, everything has degree 3. Maybe I should draw maybe a slightly more interesting example. That one's a little too easy. So let's suppose we had this graph. I'm going to make a little triangle here, and then I'm going to stick out a end on the right there. And then I'm going to kind of build out a trapezoid here, something like that. And I know I'm going a little fast, but you can always pause the video if you need more time to kind of draw this graph. We'll draw something like this. This is a little more interesting. This graph has 4 regions in it. And let's figure out the degrees of each of these regions. So obviously I see a little triangle here, so that would have degree 3. What about this sort of off-kilter trapezoid, right? I've got, you know, 2 edges on the top. I've got the 2 sides, and then I've got the base. That's actually a total of 5 different edges that are building that particular region. The one here on the bottom, ordinarily I would just call that a triangle, but it does have one interior edge. The interior edge contributes twice to the boundary of that region. So in addition to the 3 sides of the sort of exterior triangle, I have 2 more degrees added by the interior edge inside that triangle, and that's a total of 5. Okay? And then what about on the far, far, far outside? Well, let's just count how many edges it takes to go all the way around the exterior of this picture. 1, starting from the bottom, go to the left here. 1, 2, 3, 4, 5, 6, 7, right? Well, that would be 7 exterior edges for that region that's sort of outside of the whole picture. So that's maybe a slightly more interesting example. So that's the idea of the degree of a region, and we're going to have sort of a handshaking theorem type of result for this as well. You remember that the handshaking theorem told us that you know, every edge contributed to the degree of both of the vertices that it was incident with. That was our original handshaking theorem. Well, now we find out that every edge also contributes a +2 to the boundaries of the regions. And those boundary edges of those regions are really what are piling up the degree of the regions. So actually, this is a very similar type of result to what we had for the handshaking theorem, except now instead of vertices, it's going to be edges that we're looking at. If we add up the degrees over all of the regions, we're going to get 2 times the number of edges. Okay, so just the same kind of thing that we had for the handshaking theorem. Okay. Great. I think this is the first thing I needed to explain. Okay. Now, a little bit of notation here. I'm going to let n be the number of vertices in our graph. I'm going to let little e be the number of edges in the graph. And then I'm going to let little r be the number of regions in the graph. And I'm just wondering what the relationship is, if there is any relationship between these. It seems like there might be, because the degrees of the regions are related to the number of edges, and the vertices also have connections with numbers of edges as well. So it's kind of an interesting thing. Let's look at the 2 examples that we have on the board already. I think I'm going to go back and label what the values are. So this first graph has n equals 4. There's 4 vertices there. And the number of edges in the complete graph is actually 6. And the number of regions, 1, 2, 3, and then the outside region is 4. We're counting the outside region as being one of our regions, okay? So these are the values on that first example. Okay, let's look at the second example and see what the values of n, e, and r would be here as well. The number of vertices, let's count them out. 1, 2, 3, 4, 5, 6, 7, 8. Right? And then the number of edges, we could use the handshaking theorem. I'm just going to go ahead and count this out. There's the 7 edges around the outside that are already being mentioned. And then we have this one interior edge, that's 8. And then these 2 across here would be 9 and 10. So I should have 10 edges if I'm counting it correctly. And then we have 4 regions as well. So those are the values of n, e, and r. So I don't know if you want to pause the video and see if you can think of any relationships between the n, the e, and the r. But there is one here. And both of these examples support it. And it's a formula that's pretty famous. So feel free to stop if you'd like to and see if you can kind of guess what's happening. Another way to sort of play this game would be to say, oh, well, what if I added, I take this first graph and I add another edge out here. If I do this, right, then I'm adding 1 to the number of vertices and I'm adding 1 more edge. So then our numbers would be 5, 7, and 4, right? So that's one idea. Or maybe we could also decide to add another edge here. Now this time I did not add anything to the vertices, right? I just added this edge, so the n is still 5, and the edges has gone up to 8, but the number of regions has now increased, right? I have this far outside region as a separate region from the 4 that are already listed in here. So the number of regions would have gone up to 5, you see. Every time you add an edge to a graph, you're either going to be tacking on a new vertex or creating a new region, as it turns out. And that's actually the proof behind this theorem. I'm kind of proving it before I state it, but I want to get it stated here. And again, if you feel like pausing the video to check this for yourself first, feel free to do this. This is a famous result called Euler's formula. And I want to just make sure that I actually have the number right. I do not. It's actually theorem 12.2.1 in Rualdi's introductory combinatorics book that I'm giving this lecture out of. And it is called, as I said, Euler's formula. And what it says is let G be a connected planar graph. So suppose you have a connected planar graph, then, so I've given you plenty of time to think about it. So now I'm going to go ahead and spill the beans. If you take the number of regions and then subtract the number of edges and then add the number of vertices, you will always get 2 as the answer. It will always be equal to 2, which is quite remarkable. It's quite remarkable. You can just check it with all of these examples that we've kind of been playing with on the board. The number of vertices minus the number of edges plus the number of regions is always equal to 2. Okay. So that's, of course, assuming the graph is planar. If the graph is not planar, we don't have regions. And so this wouldn't even make sense to talk about this theorem in that case. Okay. From that, from the Euler's formula and this fact here, I think I am going to postpone the proof of this until a little bit later. It is something that I think we should be able to prove. You basically do the proof by induction, kind of the way I just described a moment ago. You take a graph that's not got very many vertices, edges, or regions, and then you start adding edges to that graph. And every time you add an edge, which means you're subtracting one more value here, you're either going to make one more region or make one more vertex, right? So you balance the left side of the equation every step of the way. And so you can inductively do this process one new edge at a time, preserving this statement all along the way. That's the sketch of the idea of how the proof goes, but I'm going to leave that for the time being so that I can get to some other really cool facts about planar graphs as well that we're going to want to know. So here is a fact. If G is connected, planar, and let's assume it has more than one edge. That's not a terribly heavy assumption, right? Most graphs have more than one edge in them. If a graph only has one edge, there's really not a lot to say about it. But then here's the amazing thing. You know, the intuition is that if you're going to have a planar graph, it shouldn't have too many edges. The more edges your graph has, the less likely it will be that you can redraw that graph without any crossing edges, right? So it makes sense that there should be sort of a maximum number of edges that you could have. And it turns out that there is a connection. The number of edges in your graph can be at most 3n minus 6 of all things. Right. So that's interesting. For a planar graph, your edge versus vertex relationship would have to obey this relationship here. The way this is often used is actually in sort of the contrapositive approach. If the number of edges is more than 3n minus 6, then your graph either isn't connected or it isn't planar. Let me give you a quick example of that, and then we'll prove this fact. Let's look at K5, right? K5 is going to look like this when I give this sort of the standard representation of it. It's got sort of a star in the middle and then the pentagon on the outside. That's a graph of K5. And I've mentioned before that this graph is not planar. But it might be hard to think about how you could prove that because, you know, you can try to move some of these edges outside and reduce the number of crossings. You'll never fully be able to do that, but you'll also leave some doubt, right? The skeptic, the mathematician who's a skeptic is going to say, wait a minute, just because you tried for 5 hours to redraw this graph without any crossing edges doesn't mean that the graph isn't planar. I need something more rigorous that I can go with, right? Well, if we look at this graph, obviously we have 5 vertices here, right? And we have 10 edges, right? Because there's the 5 on the outside of the pentagon, and then there's the star in the inside, which also has 5 edges, right? And if we calculate, so given the n value that we have, 3n minus 6 is actually 9. And so in this case, the number of edges is not less than or equal to 3n minus 6. This inequality fails. So this is what I mean, we're using this in the contrapositive. This inequality fails, which means the assumption fails. Well, obviously this graph is connected, so that's not what's going wrong. It obviously has more than one edge. The only thing that could possibly be going wrong right now is that this graph, K5, is not planar. So by the contrapositive of the fact above, K5 is not planar. And that is a rigorous justification that nobody can quibble with or have any doubts about. We're using the theory to really disprove this here. Okay? All right. It's interesting, if we had just one less edge, we wouldn't be able to make that contradiction, right? But we do have enough edges here. 10 edges is more edges than the number 3n minus 6. Let's prove this fact. It's kind of a tantalizing result, and you might be wondering, how in the world can we make this fact work? Well, we are going to use the earlier fact over here that was more or less adding up the degrees of all the regions gives us twice the number of edges. I want to use that right off the bat. So we can write 2e as the summation of the degree of capital R, where R is a region. Now, every region is going to have at least a degree of 3. The only way you could have a region of degree 2 would be if you had just one single edge, like this. If I had just one single edge here, then that's just one region and it would have a degree of 2. But if I add anything else to this picture, some other edge, now the degree of this region becomes 4, right? So it's at least 3, because each of these edges contributes 2 to the degree of the outside region, which is the only region that you have here. Anyway, so this is at least 3 times R. I'll just say, since we have more than one edge, it was assumed that the number of edges was more than 1 in this fact, and that's kind of where we use that. Okay, so I've used the first fact over here, but now I'm going to use the Euler formula as well. The one on the bottom here that says R minus E plus N is always equal to 2. Let me start with 2. 2 is equal to R minus E plus N. And you can see from this little equation here, guys, that R is less than or equal to 2/3 of E. Do you see that? If I divide by 3, here, I'll have R less than or equal to 2/3 of E. What I'm doing is getting rid of the R from my formula right now. So I'll have something like that. And of course, 2/3 of E minus E is negative 1/3 of E. And we add N to that, like so. And so there you have an inequality already in front of you. Let's move these terms around a little bit. Just to clean this up a little bit, I'm going to put the 1/3 E on the left side, and I'm going to subtract 2 to the right side. So we'll have 1/3 of E less than or equal to N minus 2. And therefore, when I multiply through by 3, the number of edges is therefore less than or equal to 3n minus 6. Okay. Great. Hopefully that makes a little bit of sense so far. Yeah, now I have sort of an improvement of this fact that I just wrote down that I want to also share with you. Because sometimes we can do an even tougher inequality than the one that we have on the board here. So I'm going to create an even better one. The downside to this fact, can I just number these facts? I'm sorry. Call this one, I'm going to call this one fact 1 and this one fact 2, just because they are related to each other. So add 1 and 2, I want them to kind of be thought of together. The idea here, this fact will be an even stronger inequality that can be used in the contrapositive even more effectively. The problem with it is it doesn't apply to as many graphs as this one does. So let me give you an example what I mean. So if G is connected, planar, E is greater than 1, and one more condition, G has no 3 cycles, right? Then E is actually less than or equal to 2n minus 4. That's even tougher than the original inequality. But you see, I would not have been able to use this fact on K5 because K5 does have some triangles in it, right? It has, if I see a triangle in the graph, that's a 3 cycle. So any graph that has a 3 cycle would not be eligible for us to use this fact with, okay? But in a minute, I'm going to give you a great example. Maybe you can think right now of some graphs that you know that don't have any 3 cycles in them, because if that's the case, you have an even better shot of being able to show that that graph is not planar, because this inequality is actually even more likely to fail than this one is. Guys, if you take the number of vertices and you multiply it only by 2 instead of by 3, that's actually means this right-hand side is a much smaller number now, and it's much more likely that your edge count is going to exceed that, right? So the first things first, how would the proof of this compare with the proof of fact 1 here? Actually, it's the same proof, except that the degree of every region, if there's no triangles in the graph, then there's actually no regions of degree 3. In that case, the minimum degree of any region becomes now 4, right? If there's no 3 cycles, then the degrees of your regions are going to all be at least 4. So I am going to basically just bust out a carbon copy of the same exact proof, except where I wrote 3R over there. Now I'm going to write 4R. And I'm going to go right to the same Euler formula again. 2 is equal to R minus E plus N. This time, R is less than or equal to 1/2 of E, right? So instead of 2/3 of E, I'm putting 1/2 of E here. And now I'm going to basically do the same. Well, let's just clean this up slightly. Excuse me, this is negative 1/2 E plus N. Now let's just move the 1/2 E to the left side. Subtract the 2 over with the N again, just like we did before. And if I now multiply through by 2, I get E is less than or equal to 2n minus 4. It's the same proof. It's the same proof. The only difference is the minimum degree of a region is 4 instead of 3. Okay. Right. You can imagine that if my graph had no 3 cycles and no 4 cycles, that I could tweak the proof again and get an even better bound on the number of edges in a planar graph. So it just depends on, the more assumptions you put in about your graph, the less applicable the result is. However, the advantage is that it's a pretty good result, right? It's a better and better result as you go along with that. Now, let me give you an example. Do you guys remember we proved recently that bipartite graphs can only have cycles of even length? A bipartite graph cannot have any 3 cycles in it. So in particular, let's look at the complete bipartite graph, K33, right? So this is the graph that has 3 vertices in each camp, and I'm going to create every possible edge between those vertices, just like this. So here's our graph. So we create all of those possible edges, and by the way, you can see that the number of edges is 9 here, and the number of vertices is 6. Now, if I were to try to prove that this graph is not planar by using fact 1, it wouldn't work, because the number of edges, which is 9, would be less than or equal to 3 times 6 minus 6, right? This would be 9 less than or equal to 12, no contradiction there, right? So, of course, if there's no contradiction, that doesn't mean that the graph is planar. It just means I can't use this fact to show that it's non-planar, right? The jury is still out. I don't know in this scenario, based on fact 1, I don't know whether this graph might possibly be planar or not. But what happens, guys, if I use my better fact 2 on it, right? If I take 2 times n minus 4, so that's 2 times 6, which is 12, subtract 4 from that, I get 8. 9 is not less than or equal to 8. So by the contrapositive of fact 2, right, K33 is not planar. You might as well not even try. It's not going to be planar. So K5 was not planar by the contrapositive of what I'm now calling fact number 1. Guess I should put that in the notes here, right? And K33 is not planar because of fact 2, right? Now, I guess I'm going to erase these facts here. Just going to wrap up this video with a couple sort of high-level observations, if that's okay. The first one is that any graph that contains either K5 or K33 as a subgraph would also fail to be planar. Right? As soon as there's a part within the graph that you can't remove the crossing edges from, then if that's part of a larger graph, well, those crossing edges are still there, even as part of that larger graph. You won't be able to remove those crossings. So just as a remark, any graph containing K5 or K33 as a subgraph is not planar. Okay, so if K5 or if K33 is a subgraph of something larger, the larger graph would not be planar either, right? So for example, K6, K7, K8, any of those are all not planar because they've got K5 inside of them as a subgraph. Or we could go with, K3, 4, K3, 5, K4, 4. Any of these complete bipartite graphs, as long as the M and the N are both at least 3, those are not going to be planar either. So I've got lots of examples of graphs that are not planar now, right? The really big result and the surprising result that I'll talk more about in the future is so-called Kuratowski's theorem, which basically says any graph that's not planar must either have a K5 inside of it or a K33 inside of it. Now, the statement has to be polished up just a little bit. It's not quite as simple as just saying that the graph would have a K5 subgraph or a K33 subgraph. There's slight little language tweaks that we need to do to that, but more or less, that's the intuitive way to think about it. If you're looking for an if and only if theorem, G is planar if and only if something, well, the something is approximately going to say that there should not be a K5 or a K33 as a subgraph of it. As long as that's not the case, your graph is going to be planar. So that's exciting. It's a big result. It's not necessarily obvious, but it's something that is actually true. What we've done here is we've demonstrated sort of half of that Kuratowski's theorem, right? Namely, that if we have a K5 or a K33, those are not going to be planar, right? The more challenging aspect of Kuratowski's theorem is to say, well, hey, if you took any other random graph that was not planar, it actually couldn't be all that mysterious. It would have to have a K5 or a K33 as a subgraph. That's kind of a surprising result, I think. It's actually quite interesting. So I'm going to leave it at this for now. I hope that some of these edge analysis arguments that we just made here have resonated with you. I hope it makes sense to you. They are really cool results, I think. So enjoy, keep studying. Let me know what questions you might have about this, and I'll look forward to seeing you guys all again very soon. Bye for now.